Hey there, my name's Winslow Hansen. I'm a scientist at the Cary Institute of Ecosystem Studies in upstate New York. We're a nonprofit ecological research think tank. You can think about us like an ecology department at a university, but without the rest of the university around us. And I particularly focus on trying to understand how forests and fire regimes in Western North America are likely to change over coming centuries, both from the perspective of having a deeper understanding of the ecosystems that we love, as well as to inform decision makers who are tasked with stewarding our ecosystems and human communities through this time of abrupt change. So I was tasked with answering the question, can you use models to study the impacts of wildfire and climate change on forests? And I sure hope so, because that's what I spend my whole life doing. So if not, then I'm wasting a lot of time. But I thought to get into this question, I would provide just a couple slides of context so that people can really understand why this is so important. As I mentioned, I work in Western North America and specifically focused on understanding how climate change is affecting fire regimes and what that means for our forest ecosystems. For anybody that's lived out west or has access to a newspaper, you know that the damages from fires, both to human communities as well as ecosystems, is increasing in recent decades. Just a few examples to highlight what I mean. In Oregon in 2020, the Labor Day fires burned thousands of structures and actually led to a class action lawsuit against the utility company that was responsible for those ignitions. They actually have gone out of business because of this. In California, the Camp Fire infamously consumed the entire town of Paradise and produced vast quantities of smoke that choked out the Bay Area for weeks. In Colorado, the Grizzly Creek Fire burned above an interstate, causing massive landslides that closed down that interstate for 2 weeks and led to millions of dollars of damage to infrastructure. And then a final example is in New Mexico. The Las Conchas fire burned huge swaths of beautiful ponderosa pine forest. And because the conditions after that fire were too dry to foster tree regeneration, this ecosystem has permanently converted to grassland and shrublands. Now, we all know that fire is a critical Earth system process. It's been something that's burning our forests for, millions of years. But with climate change in forests of the West, we're seeing rapid increases in burned area because conditions are getting hotter and drier. So work that we've done has shown that since 1984, the annual area burned by fires in the West, in millions of acres here, has increased something like 1,300%. 2020 is currently our observational record and is just extraordinary relative to all other years. Now, why are models useful for this? Well, what we really want to try to understand is how fire and forest regimes are going to change into the future. That's because forests change slowly relative to many different types of systems, and we care about what forests are going to look like in 2050, 2060, and even 2100 when our kids will be recreating and benefiting from the water resources, the carbon storage that forests provide. Now, process-based simulation models specifically are useful for these types of questions because the changes we're expecting to see in the future are so different from anything we have in the past observational record that we don't have good data to build statistical models of this process. They could break down in the future. And why process-based models are different is because they actually try to represent the individual processes based on first principles of biology and physics of how our forest ecosystems and fire regimes are structured and function. And because they're based on those first principles, they may be likely to be more robust under future and novel conditions. So here we're looking at an illustration of a process-based model that's trying to simulate a forest stand. And you can see there's trees of different sizes that are interacting for light and above ground resources, below ground resources. These are the factors that drive models into the future. So how are we using models to try to understand how forest and fire regimes might change into the future? Well, different models are appropriate at different scales, and we're linking together models all the way from the individual tree to the forest landscape to the entire Western US region. And we're dynamically coupling that with a monthly fire model that simulates the numbers of fires and their maximum sizes each month as a function of climate, human conditions, and fuels. And by doing this coupled set of models, we can actually make joint projections of how fire and forest regimes will change into the future across this domain. So on the right here, we're looking at a figure. This is many model simulation runs from this model forced with a moderate climate change scenario. And we're looking at how much area is likely to burn each year through 2100 under this scenario. You can see that there's massive increases in burning. So for a benchmark here, this is the area that burned in 2020, our current record in the observational period. And you can see by roughly 2050, the area burned each year on average is about our record of 2020. So massive increases in burning. But what's so important here is that we're also dynamically simulating how forests are responding. And that's really important because fires aren't just affected by climate change, they're also affected by fuels. And so if you get a lot more fire on the landscape, it could be that fuels become so limiting that it constrains the amount of area that can be burned, even if climate change is extreme. So this projection of future fire with these massive increases is already including those negative feedbacks from reductions in fuels. What this figure highlights is that we are likely to see profound increases in burning, even when accounting for limitations in fuels. It's going to be a more fiery future. The last benefit of using a process-based simulation approach to make these future projections is we can run what we call counterfactual scenarios or experiments, where we actually ask what-if questions. For example, we could ask, what if we try this management strategy versus this management strategy, and then compare those outcomes in terms of burned area and forest dynamics to this baseline simulation where only future climate and fuels are having an effect to see the efficacy of our management. So in conclusion, we desperately need insights into how our ecosystems and our fire regimes are likely to change into the future. And process-based modeling, while not perfect, is the best tool that we have for making those future projections as robustly and scientifically rigorously as possible. Thanks so much. I hope you enjoy.